안녕하세요 여러분, 해리입니다. So in the last video we have finished studying arithmetic series. So in this video we're going to start with geometric series. So geometric series is a sequence of numbers with a common ratio. So an example can be something like this, so 1, 2, 4, 6, 8, and so on, where the common ratio for this case is 8, 16, and so on, and the common ratio for this would be 2. Or we can have something like 1 negative half, 1/4, negative 1/8, and so on. And for this one, the common ratio will be negative half. So like what we did for arithmetic series, let's try to derive the equation for the general term by investigating an example of geometric series. So let's consider this case. So 1, 2, 4. So again, this one here will be the first term because we started from 1, and this one will be second term, third term, and fourth term, and so on. So how do we find the second term? We start from the first term and then we multiply the common ratio once. So for this case, the common ratio is 2, right? So that means from the first term, we multiply one common ratio. For the next term, how we can compute it is that we start from the first term, we multiply one common ratio, and we multiply another common ratio. So simply, we have this equation, and it will be the same for the fourth term. So start from 1, multiply common difference, common ratio, and another common ratio. So we will have this. Then if we extend this to nth term, what we will have is that we will have the equation of un, which refers to the nth term, as u1 times r to n minus 1. So why is it n minus 1? We can see that for the fourth term, we have 3 common ratios. Third term, we have 2 common ratios. Second term, we have 1 common ratio. So nth term, we will have n minus 1 common ratio multiplied. Okay? So we can find the general equation using this inductive method reasoning. Okay, so let's try some examples. I'll keep the example simple at this moment. So let's say we have a first term 4 and the last term 2000 something like this, and the common ratio as 3, and we want to find n. Then so we know the equation of un, right? So the nth term will be the first term times common ratio to n minus 1, and that equals to this number, right? So we divide both sides by 4. That will be this. So 729 is 3 to 6, right? Because that's 27 squared. So that means we can see that n equals to 7. Okay, so shouldn't be that difficult. So another example can be something like this. So common ratio as half, fifth term equals to 20, and find the first term. Then again it's same, so we just use this equation. Alright, so we just write down the equation for the general term, and then we substitute the values that we know. So we know the fifth term, right? So that means and we also know the common ratio, right? And we know this value already, which is 20. So that means u1 equals to 20 times 16, which is 320. Okay, so it's very simple arithmetic. One last example is where we have 3 consecutive terms, not necessarily 3, but consecutive terms of geometric series. So like what we had for arithmetic series as well. So remember this example for arithmetic series. We have 3 terms, 3 consecutive terms, and we use the idea of common difference to solve this problem, right? And let's do the similar thing for a case where we have 3 consecutive terms of geometric series. So let's say so what we can do is that since these terms are from geometric series, and since they are consecutive, that means the division of these two and these two will be the same. So how do we find the common ratio? We can find the common ratio by dividing the previous term from the next term, right? So this is what we will have for the common ratio. And we can also find common ratio by dividing x from 1, right? So that means we will have a quadratic equation. So we will have x equals to 2 or x equals to -1. So let's quickly check whether they actually form geometric series. So when x equals to 2, then it's 4, 2, and 1, and it makes perfect sense because the common ratio is half, right? When x equals to -1, that means 1, -1, and 1, and still this is also a geometric series. The common ratio is just -1, okay? So it should be very simple, right? So then let's move to sum. Unlike in geometric series, unlike in arithmetic series, the derivation of sum of geometric series is a bit more complicated. I'm going to explain it as well, but you need some good technique of factorization. So let's use the symbol again, Sn. So it means that we're adding the first nth terms, right? So basically what this is saying is that we add from u1, the first term, to un. So no matter whether a series is either geometric or arithmetic, they both work. So that idea still works because Sn is just saying that it's just a sum, okay? Doesn't matter about the type of the series. So this is what it means. And since we're looking for the sum for geometric series, then why don't we write all these other terms in terms of u1 and the common ratio as what we had from the formula for the general term, okay? So that means u1 plus u1 times r plus u1 times r squared, right? And we add all the way until u1 times r to n minus 2, right? Because n is n minus, so we have n, this is the n minus 1th term, so that means we have n minus 2 common ratios. And lastly, we will have this, right? So for this one, what is a common factor? So common factor is u1, so we can take it out by u1. I factorize out by u1. So this is what we have. And note that we don't want something like dot 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 in the formula, right? So what we can do is that we can use one of the properties. So if you remember this, some may remember this. So why don't we just consider b as 1? We will have this, right? Then what about a to the 4 minus 1? You will have this. Then what about a to the 5? Again, you will have a very similar expression like this. Then what if we have n? Then we will have a minus 1, a to n minus 1, right? So that if you multiply these two, we will have n. And we have all the way until a plus 1. And what is this? This, the equation that we want, right? Then that means we can write this as r to n minus 1 over r minus 1, right? So the sum of the geometric series is defined like this, okay? And for the case where r is less than 1, so in that case we don't want a negative value in the denominator. So what we can do is that we can just write it like this. And this still works because what we did is that we factorized this by -1 and we factorized this by -1 too. So the two negative ones cancel, so we will have this result, okay? And it shouldn't be difficult, I hope. Maybe we can try an example. So let's say, so we don't have enough space for this, so use another paper. So let's say and we want to find the sum. Okay, so for this one, what's the common ratio? The common ratio is half, and the first term is 3, right? That means the sum of nth term will be u1 r to n minus 1 over r minus 1. But we see that r is less than 1. So you can still use this, but I prefer using this when r is less than 1 because I don't want any negative value. So I can substitute the values that I know. Like this. But we have a problem because we don't know what n is, right? Then how can we find n? We use the general term because we know the last term, right? So the last term, which is the nth term, will equal to the first term times the common ratio to n minus 1, right? So the 3 cancels, and 2048 will be, so it's good to memorize some like numbers with powers. So 2 to 10 equals 2024. So that means 2 to 11 is 2048. So that means n equals to 12, right? Then we just quickly, we can evaluate this value. And you may use your calculator to evaluate this, or you can just go for 1 over 4096 and then try. So yeah, and that's it for the example. One more thing about geometric series is that unlike arithmetic series, where we cannot find the sum to infinity, for some specific geometric sequences, we can find the infinite sum. So infinite sum of geometric series. But before that, what does it mean by infinite sum? So it means that we are adding the terms to infinity. So that means, again, we start from u1, we add the second term, we add the third term, and there is no limit. We are adding on and on and on. So we cannot write something like this. We can't. So there's just no limit, okay? So how we can find this is that we can use the formula from what we had just now. All right, so here, let's consider when r is greater than 1. So for example, r equals to 2. Then when n tends to infinity, that means when n is a really large number, what happens to the sum? It will become very large too, or negatively large, right? Then what if the common ratio is between 1 and -1? And note that r cannot be 1 because, as you can see, that if r is 1, well, first, if r is 1, it's not a series. I mean, it doesn't have any pattern, right? It's 1, 1, 1, 1, 1, 1, 1, or like 3, 3, 3, 3, 3. There's no change, right? We don't code it as a series. So, and if r equals to 1, then the denominator is undefined, so we don't consider the case where the common ratio is 1, okay? So, and also r cannot be 0, because if r equals to 0, then again it's not a sequence, because for example 3, we start with 3 and it's just 0, 0, 0, 0 all the way, right? So that's not a sequence, that's not a geometric series. So let's say r is between these values, so let's say half. Then if you multiply half many times, like for example 1,000 or like 10,000 or even like 1,000,000 times, then what happens to that value? It becomes really small, right? So small that it is almost negligible, right? So what we can do, what we can think that s to infinity, so sum to infinity is simply u1 times 1 minus 0 over 1 minus r. Because r to n gets so small that we can treat it as 0. So this is the equation. This is the formula for sum to infinity. So an example is something like and we want to find the sum to infinity, then it's very simple. You know the first term, and you know the common ratio, which is half, then it's just 6. Okay, so that's it for the geometric series. That's it. But for HO students, you'll have a lot of like not only HO but so geometric series in general. The most difficult case that I can think of is probably when we apply the concept of geometric series in finance. So for example, when you have to like calculate some compound interest of like certain product from banks. But for those examples, I'll put them in the sample test and then I'll let you try by yourself. And I'll also explain how we can solve analyze those problems. So before we finish, one more thing in series. So the notation for sum, which is the sigma. So I'm pretty sure you may have seen this symbol a lot. So this symbol means we are adding up certain things. But so in order to use this symbol, we need the boundary. So where do we add? So where do we start to add and where do we finish? So for example, if the previous case for Sn, let's not use S infinity. So for Sn, so that means we're adding the first term, second term, all the way until the nth term, right? And we can actually use this sigma notation to write this without using this dot dot dot. So what we can do is that we can find the pattern first. So this value, the underscope value, is increasing by 1, right? 1, 2, 3, and all the way to n. So we know the starting point and we know the end point, right? So that means we can say the boundary starts from 1 to n, and we're adding uk. So what this means is that sigma, again, it's telling that we're adding up these, right? This, and from where to where when k equals to 1 to n. So that means when k equals to 1, that's u1. When k equals to 2, that's u2. And when k equals to 3, that will be u3 there. And all the way until when k equals to n, where we add un. Okay? So this is the basic so this is the notation for the sum, and there are some properties which are very useful to know. So when you have a constant with a series multiplied, then you can just take out the constant like this. Why can we do this? For example, for this one, let's say Sn equals to Cu1 plus Cu2 plus Cu3 and all the way until Cun. Then we can factorize this by C, right? And what is this? It's just the sigma, right? But how do we write this using sigma notation? This is how we can write it, because every term we have C, and then we see that the series here, the underscope value increases by 1, right? And we start from 1 to n. So we can do this, okay? We can take out the constant when it's multiplied. Just multiplied, not added, multiplied or divided. Second, so when you have a multiple terms, like this, then what you can do is that you can just add them up separately. Because note that addition, does the order matter? And the answer is no, right? So that means instead of just adding uk and ak together, so u1 plus a1, u2 plus a2, u3 plus a3, and all the way until un to un plus an, then why don't we just add the series from u first, and then we add the series for a separately, and then add them up, right? That still makes sense. And it's the same for the negative sign as well, a subtraction. And last thing that a lot of students misunderstand is that what if we have a constant? And many of you say just C, and in fact the answer is C times n. Why? So remember the definition of sigma. So sigma, again, it's saying that we're adding this from k equals to 1 to n. But you may say that there is no k, right? Well, that means it doesn't really matter, because what this actually means is that it's telling you the number of term. So when k equals to 1, it simply means it's the first term. And when k equals to 2, it simply means it's the second term. And when k equals to 3, it's simply saying that it's the third term. And when k equals to n, it's the last term. So that means how many c's have we added? We added n c's, so we have c times n. Okay, so these are the basic notations for sigma. And let's try an example. So for HO students, there's one assumed knowledge that when you have to add the square numbers, so the formula is like this. So n times n plus 1 times 2n plus 1. And how do we derive this? Well, I will not really ask you to derive this, and I'm pretty sure you will not be asked to derive this either. But so if you know, so square numbers are also an example of sequence of differences, because we're basically adding all these terms, right? And we see that the difference follows arithmetic series. But you haven't learned the sum of sequence of differences. You learned this in recursive sets, recursive relation. So like in discrete mathematics HO option. So for this derivation, I'll give you a hint. You may try evaluating the values for k equals to 1, k equals to 2, k equals to 3, and so on, and then see whether you can derive this. Okay, so this is a hint. For the proper derivation, I'll put it on the inside the sample test. Okay, so let's try an example. For SL students, we have to study this sigma notation as well, so you need this as well. But just this is for HO. So let's say we want to find this value. So if you guys are not really familiar with sigma, what you can do is that you can expand it out. That's absolutely fine too. So when k equals to 1, that means 2 plus 3 plus 1. And when k equals to 2, 2 squared plus 6 plus 1. And when k equals to 3, 2 cubed, 9 plus 1. And all the way until 2 to 20 plus 3 times 20 plus 1. One thing, I don't really recommend you to evaluate this entire value first. So don't write it like 6, 11, and 18, so on. You can just leave it like this, because what we can see is that it's this, right? Because again, addition, the order doesn't matter. So what is this? It's a geometric series with the first term 2 and the common ratio 1. So directly, and we also know the number of terms. There are 20 terms, so we can directly compute the value out, right, using the equation of the sum. And we can also this is an arithmetic series with the first term 3 and the common difference 3. So, and there are 20 terms too, so again we can directly use the formula as well. And that means we add 1 20 times, so that's just 20. So this is what you will have. But let's try to use these sigma properties if you want to use sigma, then what we can do is that we have 3 terms, right? So that means we can just add term by term. Okay, so this is method 1 by expansion, and method 2 by sigma. Well, but for method 2, you still need to expand it out, to be honest. I mean, you don't really have to expand it, but you still have to use the formula for sum of geometric series and sum of arithmetic series. But one thing is that you don't have to do this, okay? So we know that we can kind of distribute the series like this. And this, we can see that it's a geometric series because for each term, it's just being multiplied by 2, right? The common ratio. So this is sum to geometric series. And for this one, we can take 3 out and then add k. That means, so this is what we can do. And this one, we know that it's just a constant. So constant times the number of terms, which is 20. And what is this? It's simply adding 1 to 20. So again, it's the arithmetic series. So sum to geometric series plus 3 times sum to arithmetic series and plus 20. And you will have the same value, okay? So that's it for the series. And yeah, this is probably it. But one thing to specify a bit more is about infinite sum of geometric series. So I have passed too quickly. So I'll explain a bit more about this condition. So usually the condition is in like that. Well, it's the same thing. So there could be a question like this. So let's say there's a geometric series like with a common first term 4 and common ratio of 3x plus 1, let's say. Then the question is that find the values of x such that this geometric series have infinite sum. So what we can do is that in order for a geometric series to have infinite sum, then its common ratio must lie between -1 and 1. So the common ratio here is 3x plus 1, right? So that means 3x plus 1 must lie between 1 and -1. So that means 3x is from 0 to -2, and x is just from 0 to -2/3. Okay, so this is how we can find the values of the common values of an unknown variable in the common ratio when we have to find the infinite sum. Okay. Right, so that's it for the series. And again, the examples that we have tried are probably the easiest, the simplest examples. So please try the sample tests. I will include very difficult questions as well. Okay, so that's it for series today, and see you guys in the next video.